Today we're going to start focusing.
The leader has muted your line. To unmute your line, press #6.
All right, are you hearing me, Michelle? All right, let me try again. Can you hear me now, Michelle?
Has unmuted your line.
And can you hear me, Michelle?
That I can. Hold on 1 second, sir. I'm going to try muting you again. I just got a weird glitch on the phone. If you can hold on 1 moment.
Okay.
I'm going to mute you one more time. We'll start over, and then you'll have to unmute yourself.
Okay.
There you go.
The leader has muted your line. To unmute your line, press #6.
So hopefully I'm getting pretty good at unmuting my line. And you can still hear me, right?
Correct.
Okay. So in January for the Intro to Crypto, that was a very generic session just talking about crypto in general. Today we're going to start focusing in a little bit more on the IBM crypto infrastructure and start off by talking about the hardware. Now there's a lot of territory to cover, so we're going to cover hardware in both February this week, and then again in March. So hopefully everybody can see that I'm on slide 2 in the presentation and on the webcast. We're going to touch on a couple of the slides that we touched on in January just to get everybody up to speed and thinking along the same lines, a little bit of a refresher. I want to talk a little bit about a history of crypto because I think that'll help you understand a little bit about where we're going. And then we're going to talk about some terminology. There's the IBM hardware has been defined as clear key or secure key, and I want to make sure that people understand that. And then from there, we'll focus in on the first bit of IBM hardware, the CP Assist for Cryptographic Function, or the CPAC-F hardware. Next month, in March, we'll focus on the Crypto Express cards, the additional features that are available. So on slide 3, again, this is a chart that we saw last month. It describes cryptographic functionality. Nothing here specific to IBM so much, but these are the functions that are available via the cryptographic infrastructure. The first 2 on there are under data confidentiality. That's what people typically think of when they think of crypto. It's the idea of hiding data and making data look like garbage. And we learned last month that there's 2 types of algorithms available. There are symmetric algorithms, which are algorithms where both parties have a copy of the key material. So if I want to send data to somebody on the phone, I've got to select a key. I've got to somehow transmit that key to my partner, and then I can encrypt data with the key, send them the ciphertext, and they can decrypt it using the same key. Asymmetric algorithms, on the other hand, rely on 2 different but mathematically related values. I can perform encryption using one key, and my partner can decrypt using the other key. And that provides some integrity. Alternatively, my partner can encrypt data using my public key, and multiple people can encrypt data using my public key. Each of them can send me their ciphertext, and I can decrypt that data using that corresponding private key that's associated with the public key. There's a bunch of different symmetric algorithms that are available. The ones listed on the chart here are the ones that we support on the IBM hardware, and we'll talk a lot more about that as we go along. The asymmetric algorithms, we support all 3 of those algorithms in the hardware, but mostly on the Crypto Express card, and we'll see more about that next month. The additional functionality includes the concept of data integrity. Modification detection is the idea of whether I can tell whether a message has been changed, either accidentally or deliberately, so that if I send a message to you, can you tell that the message you received is the actual message that I sent? And that relies on something called hashing algorithms. We also have the concept of message authentication, the idea of not only can you tell whether the message changed or not, but can you tell whether it really came from me? Do you have some confidence that somebody didn't slip in a bogus message and try and impersonate me? And then the third bullet there under data integrity is non-repudiation, and it's the idea of, can I deny issuing or initiating a transaction? That's kind of important in our web world today. If I go into Amazon or one of the online catalog stores and order a product and provide my credit card information, can I come back later and deny having done that? Of course, these catalog stores don't want people to be able to repudiate a transaction, so non-repudiation is an important function that is provided with the crypto infrastructure. Financial functions are the ATM PIN processing. If you go to your bank and use your PIN, how do we protect that PIN value? That relies on a lot of the data confidentiality algorithms, although they've been extended to provide additional protection for that PIN material. And then the last bullet on here is key security integrity. I mentioned last month that that's really important to your crypto infrastructure. If you don't have key security and key integrity, then your crypto infrastructure is going to break down. If the key values are lost or compromised, then anybody that gets access to that key material can access your data. So these are the functions that are available. What I want you to keep in mind as we go through the rest of the presentation is noticing where this functionality, what hardware provides this functionality. Because you're going to see that while the hardware does have some overlap, the overlap is really in terms of additional protection. There are some functions that are available on one device, other functions that are only available on another device, and when they do overlap, the way things work are really different, and there's some additional security and integrity involved. So with that, we're going to turn to slide 4, which provides a little bit of a history of the IBM crypto infrastructure. Now, this chart only goes back to the year 2001. As I mentioned last month, IBM actually developed the what is now known as the DES algorithm back in the 1970s. So we've actually been doing crypto a lot longer than that. There have been other hardware devices, other crypto software available pre-2001, but we're going to pick it up here from 2001. And if you'll notice, around the year 2003, 2004, the technology changed very significantly. So if you're running on a Z800 or Z900 or older, and hopefully nobody on the call is still on those older machines, they worked very differently than the hardware that's available today. In about the year 2003, when we introduced the Z990, along with the Z990 came this hardware called the CP Assist for Cryptographic Function, or CPAC-F. We also continued using the PCI cards on these machines. So just be aware that the functionality changed. If you're running on those older devices, there is a reference at the end of the presentation about one of the tech docs, a synopsis of System Z crypto hardware. It can provide you a little bit more background on those older devices. The other comment I want to make on this chart is that I think you will continue to see this chart move to the right. IBM is very committed to providing the crypto infrastructure that you need. It has become critical to most, if not all, organizations. The ability to do at least some level of encryption technology. So as it's been extended through the Z9, the Z10, now out to the ZEC12 and the ZBC12 and the Crypto Express 4S card, I think you will continue to see this chart extended going forward. So with that, we'll turn to slide 5. Again, this is some of the terminology that I want to make sure that you understand. Historically, the IBM hardware has been defined as either clear key or secure key hardware. Now, I think if IBM had a mulligan and could do things over again, they would probably choose different terminology, because it's been kind of a knee-jerk reaction that, oh, I've got to be as secure as possible. I've got to use this thing called secure key. Well, maybe you do and maybe you don't. So it's important that you understand the capabilities here. The idea with clear key hardware is that the hardware device expects to receive the key material in the clear. If you go back even prior to this hardware being available, you can implement encryption algorithms in software. You can use move characters and multiply instructions and shift logical instructions to implement the DES algorithm or the AES algorithm or RSA or ECC. But if you do it in software, by definition, your key material is going to be a value that's used in that program. So your key material is going to be in the clear in memory somewhere. Similarly, the clear key hardware expects your program to pass it the key material in the clear. So clear key hardware expects the key material in the clear. Secure key hardware, on the other hand, we provide some hardware that provides additional protection for your key material. The Crypto Express card is our secure key device today. It is what's called an HSM, or a hardware security module. We'll see next month that hardware security module means it has technology built in, tamper responding technology, so that if somebody puts a probe on the card and tries to see the key material, the card will react to that and will wipe out the security information, the key material, before it will let it be compromised. So with secure key hardware, we're providing some additional protection for your keys. Now, your keys are still going to have to leave that hardware security module at some point. You're going to want to store that key in a repository so that a week from next Tuesday, when you need it, you can bring that key material back in and use it. And the way the secure key device works is you can create a key inside the HSM, but before it leaves that secure boundary, we will encrypt it under another key called the master key. And what actually gets stored out in your key repository is the ciphertext that is your key value. So there is protection when it's outside the boundary in that it's enciphered, and then it's protected when it's inside the card by the tamper-resistant technology. And the next couple slides will get into that a little bit more. The third type is protected key. That's relatively new. That was introduced with the Crypto Express 3 cards on the Z10. It's kind of a hybrid. It relies on both secure key and clear key hardware, so that your key material will never exist in the clear anywhere except inside of hardware. But that hardware may not be tamper-resistant hardware. Again, a later slide will go into the details a little bit more, but eventually your key will be brought into the CPAC-F hardware and the crypto operation performed there, but that CPAC-F does not have that tamper-resistant technology built into it. So let's go to slide 6. We're going to talk a little bit more about clear key. Again, the idea here is your key material will exist somewhere in the clear. Now, the way it works is you might save, on this example, we're using a key value of A, B, C, D, E, F, and you might store that key in a key repository somewhere. Within ICSF, the symmetric key repository is the CKDS, or the cryptographic key data set, and your key would be stored inside that key repository in the clear. Now, when your application wants to perform an encryption operation, it'll call the ICSF API. ICSF will, on behalf of your calling program, it'll go out, retrieve that record from the CKDS, and then pass that key value to the CPAC-F hardware along with the data that you want to encrypt. Now, the nice thing here is the key material exists in the ICSF address space, not in your calling program's address space. So if the program should append, or if somebody should take a dump of your calling program, the key is not there in storage. It is, however, in the ICSF address space. So while this call is being performed, if somebody takes a dump of the ICSF address space, they could conceivably see your key material. or if they can somehow get access to the key repository, if they could browse the key repository, they could see your key value in the record there. So with clear key, your operational procedures are providing the protection for the key. You are hopefully, you have turned on SAF protection so that not just anybody can read the CKDS and see those clear keys that exist there. And you don't allow just anybody to take a dump of the ICSF address space, or for that matter a standalone dump of the system, because that key material could show up in memory in the dump. Now let's contrast that on slide 7 with the secure key technology. Again, the idea here is the key is stored in your repository after it has been encrypted under another key called the master key. And when we get into the Crypto Express hardware and then with ICSF a little bit later, we'll talk a lot more detail about how those master keys work. But the bottom line is your key value of ABCDEF is encrypted under this master key, and that ciphertext, in this case it's EFGHJK, is what's stored in the CKDS, the key repository. So once again, when you want to use that key, you want to encrypt some data with that key, your program will call an ICSF API. You'll pass a pointer to the key label in the key repository, and you'll pass the data that you want encrypted to ICSF. ICSF will retrieve the ciphertext from the key repository and then pass that encrypted key value to the Crypto Express card along with the data to be encrypted. Inside that tamper-resistant boundary, the crypto card will decrypt your key from underneath the master key, recover the original value of ABCDEF, and perform the crypto operation all inside that Crypto Express card. So if somebody takes a dump of your address space or the ICSF address space, they will not see the actual key value of ABCDEF. They would only see the ciphertext of EFGHJK. So the key material is protected. It's only in the clear once it's inside the Crypto Express card where the actual work is done. On slide 8, I'm going to describe how protected key works. Again, it's a hybrid. It uses both clear key and secure key hardware. With protected key, your key material will begin life as a secure key. So if you want to do encryption using a protected key, the first thing you're going to do is create a secure key. And as we saw in the previous chart, the way a secure key works is you would probably generate a random number, that will be your key value, and encrypt that random number under the master key. And that key material gets stored out in the key repository as a secure key. So in this example, the random number, what a coincidence, that I generated is ABCD. That's the actual value of our key. It gets encrypted under the master key, and in this case it generates ciphertext of 4 alpha exclamation mark 2. That's what gets stored in the CKDS. Now when you want to use the protected key, your program will call a clear key API, but it'll point to that secure key label. Now, prior to the protected key support, if you were running an older version of ICSF, if you did this, the call would fail because we would not allow you to use a secure key with the clear key API. But with the right version of ICSF, with the Crypto Express card to support protected key, what happens now is ICSF says, oh, this is one of those this new animals called a protected key. I can go ahead and retrieve that secure key and perform the work. So we call the API. In this case, we're calling the clear key API CSNB-SYE. And we're passing it a pointer, my key, which references the secure key, and the message that we want to encrypt, my message. On slide 9, what's going to happen is ICSF is going to retrieve that ciphertext from the key repository and pass it to the Crypto Express card. Inside the Crypto Express card, inside the tamper-resistant boundary, we're going to decrypt that from underneath the master key and recover the original value of ABCD. But then instead of performing the operation here, we're going to immediately re-encrypt that data key, the ABCD, with what's called a wrapping key. And we'll talk a little bit more about where the wrapping key comes from in a minute. But that wrapping key is then used to encrypt ABCD, and in this case we get ciphertext of *94 easy. That value will come out of the Crypto Express card, so your key is passed back to ICSF. ICSF will have the value of *94 easy in memory now, not your key value itself, but it'll pass that to the CPAC-F hardware. Inside the CPAC-F hardware, it will recognize, oh, this is one of those new animals called a protected key. The CPAC-F hardware will retrieve the wrapping key as the same wrapping key that the Crypto Express card used and decrypt this wrapped key value, recovering ABCD. Now, inside the CPAC-F hardware, we'll perform the actual encryption operation to encrypt my message using the key value of ABCD and come up with the ciphertext here that begins with 81 Fox Fox, and that's what will be returned to my calling program. So we've used both the Crypto Express hardware and the CPAC-F hardware. As we get farther along, you're going to see that clear key is significantly faster than secure key. And by significantly, I mean orders of magnitude faster. And secure key could be a problem for some performance-sensitive applications. Protected key provides kind of a hybrid, something in between. It's a little bit slower than clear key, but still significantly faster than secure key. And we'll get into that a lot more in one of the later presentations when we talk about performance expectations with the crypto hardware. But the bottom line is you have clear key hardware, you have secure key hardware, and now we have this hybrid called protected key as well. So as we go along, keep in mind that the hardware is defined as either clear key or secure key. Slide 10, I want to talk a little bit more about this thing called a wrapping key. There's actually two different wrapping keys. There's a TDES wrapping key, and there's an AES wrapping key. The DES wrapping key is used to encrypt DES operational keys, and the AES wrapping key is used to encrypt AES operational keys. The wrapping key is actually generated when the LPAR is activated. That is, when you start a new LPAR, when you activate an LPAR, part of the logic that it goes through now on the Z10s and laters is that it will create a random number that will be used, one random number to be used as the AES wrapping key and another random number to be used as the DES wrapping key. That wrapping key is stored in the HSA, the hardware storage area. It is only accessible by the hardware. You cannot access these values in the HSA programmatically, so the operating system doesn't have access to it. Your programs don't have access to it. It's only used by the Crypto Express card and the CPAC-F hardware. Now, as we saw in the last chart, your key is going to get, at least temporarily, wrapped using these wrapping keys. You are not going to want to save that wrapped key value. You're not going to want to put it in the data set. Because it's unique to the activation of the LPAR, let's suppose you had a sysplex environment with multiple LPARs sharing the key repository. Each LPAR would have a different wrapping key value. So if you wrap the key on LPAR 1, you could not unwrap that key on LPAR 3 because it's using a different wrapping key value. It's unique to the LPAR. In addition, you wouldn't save it in a data set for use later because there may not, you may have suffered an LPAR outage, or you had the LPAR be reactivated from the time that you wrote this wrapped key to a data set and then when you tried to use it. If the LPAR goes down and gets reactivated, you're going to get a new wrapping key, and whatever wrapped key value you had stored somewhere would no longer be recoverable because the original wrapping key wouldn't be available. So that's why your protected key begins life as a secure key. We save it in the CKDS in the key repository encrypted under the master key, and its only used in a dynamic environment. When you want to use that protected key, we will wrap it and unwrap it long enough to process it between the Crypto Express card and the CPAC-F hardware. So let's go to slide 11. Again, this is a little bit of the history. The CPAC, starting with the Z990s and the Z890, we have two different cryptographic hardware devices. We have the CPAC-F, the CP Assist for Cryptographic Function, and we have the Crypto Express cards. Now, back on the Z990 and 890, they were called PCI XCC cards and PCI CA cards. But with the machines today, the Crypto Express card is the secure key hardware that's available. They are installed out in the I/O cage or on the ZEC12 and BC12. That's now called the I/O drawer. So those cards are effectively out in the I/O subsystem, and when you want to do work on those cards, you are doing an I/O operation to get the work out there. So that's an asynchronous operation where you hand the work off to the Crypto Express card, wait for it to do its thing, and then return the results back to the calling program. As compared to the CPAC-F, we're going to see in a minute, that's basically just some additional real estate on your CP. So the work done on the CPAC-F is a synchronous operation. It runs at machine speeds, so it's significantly faster. So with that said, let's go into a little. We're going to focus now a lot more on the CPAC-F hardware. This is a diagram of the ZEC12. The first thing I'll point out here, this talks about a feature code number 3863. That's a no-charge feature code that must be installed to enable the crypto hardware. Now, the U.S. government considers crypto technology to be a munitions. That is something that bad guys could use to make war against the United States, and therefore they restrict who we can provide that technology to. There are a list of embargoed countries that are not permitted to have this technology. If somebody in one of those countries, like an Iraq or North Korea, if you come to IBM and want to order a ZEC12, for a small amount of money, we'd be happy to send you a ZEC12. However, we cannot legally ship to them this feature code that will enable the crypto hardware because they are in the embargoed countries. Again, this is a no-charge feature. Some years ago, when the Z990s first came out, a lot of customers did not get this feature code and install it, which meant they could not use any of this crypto technology that was available. And this feature code is a prereq to the Crypto Express cards. You must have this installed before you can use the Crypto Express cards. And there's even some software routines that will check for whether this feature code has been installed or not. And that's how we handle the embargo there as well. If you want to enable some of these routines, you must have feature code 3863 installed. Now underneath that, there's a list of the functionality, what it supports. It supports DES and AES encryption and SHA hashing. And that's the limit of what the CPAC-F support. It does symmetric encryption using clear keys, and it does hashing operations. Now, notice on the right that there's a one-to-one correspondence. Each CP has access to the crypto cipher, the encryption engines, as well as the hashing engine. So there's a one-to-one relationship. That's true on the EC12. It was also true on the original Z990, the 890, and the Z9. However, on slide 13, I want to point out that the Z196 and the Z114 and the Z10s actually shared the CPAC-F hardware between CPs. So on these machines, if you had a four-way, if you had four CPs on your Z10, you had access to two CPAC-F hardware devices. Whereas on the EC12, it's a one-to-one relationship. If you've got a 10-way EC12, you have 10 CPAC-F hardware devices available. And again, it's just some additional real estate. We'll talk a little bit more about what that means in a minute. We'll also talk about a little bit more about this implementation when we get a little bit further along and talk about some of the performance that you can expect. There was one other thing I wanted to mention on this chart, and my mind just went blank. So we'll go on to the next slide, slide 14. A lot of customers ask me, how do I know if I have feature code 3863, if I have have access to the CPAC-F hardware? This is a screenshot from the HMC. If you're the hardware management console, you can go out and look at the system details for your KEC. And notice down in the bottom right-hand corner, it says CP Assist for crypto functions installed. If it says not installed there, that means you don't have feature code 3863 installed. It's simply a matter of talking to your IBM rep and getting them to order that feature code and then getting your CE to install it. Again, it's no charge. So I would encourage everyone to have that installed and make sure that it's available. There's also an ICSF API that you can use to query the environment to see if the CPAC-F hardware is available. You have to have ICSF up and running to call the API, but that is another way to check on availability. Let's go to slide 15. I want to talk a little bit more about what the CPAC-F provides. Like I said before, it's basically just additional real estate on your CP. So your general purpose CP provides lots of instructions, like the move character instruction. The CPAC-F provides a handful of additional instructions that are accessible from assembler routines. So the cipher message is the KM instruction. It works a little bit like the move character instruction. A move character you point to storage location 1 and storage location 2, and the instruction will move data from location 1 to location 2. With the KM instruction, you point to a storage location where your clear text is, you point to another storage location where your ciphertext will go. And it will move the data from location 1 to location 2, and when it gets to location 2, it will have been encrypted using the algorithm and the key that you specify via some of the registers. So you can look up all of these instructions in the POPS manual, the Principles of Operations manual, to see exactly how they work. You can write your own assembler routines to invoke these instructions. So you don't even have to go through ICSF. And in fact, that's where you would get the best performance, is just calling these instructions natively. Now, on the CPAC-F, each generation of KEC, and we're going to go through them on the next couple slides, provide these instructions. They're called the Message Security Assist instructions. Each machine generation has been another level of MSA. The Z990 provided MSA, the Z9 provided MSA1, and then MSA2. These are the instructions that they provide. The first MSA through MSA3, the same instructions were just being enhanced from machine to machine. And again, we'll see that on the next chart. With MSA4, we have introduced some new additional instructions. Those are available on the Z196 and later. And again, when you're executing these instructions, it's just like executing a move character or a multiply instruction. It's a synchronous operation. The CP will show up as CPU busy when performing these, and they're going to run at machine speed. So whatever the capability of your platform is in terms of cycle times and all that, that's the kind of performance you're going to see with these instructions. So going through the MSA levels, again, the Z890 and the Z990 provided the first implementation of the MSA instructions. The only thing you could do on those machines was DES encryption. Now you could use single, double, or triple length keys, but you could only do DES encryption, and you could do SHA-1 hashing. Relating this back to that crypto functions chart that we saw at the beginning of the presentation, you could do symmetric DES, triple DES encryption, and you could do modification detection codes. That's all you can do on the CPAC-F. On slide 17, the next generation MSA1 was available on the Z9. We added AES encryption, but that was limited to 128-bit keys. You still couldn't use 256-bit keys at that point. We also extended the SHA algorithm to support SHA-256, which meant you could support SHA-224 as well as SHA-256. And we also introduced a pseudo-random number generator that was available in the CPAC-F hardware. Now that was written to the ANSI X 9.17 standard. There's a standard for a pseudo-random number generator, and that's what we implemented on the CPAC-F hardware. On slide 18, that's MSA2, which is available with the first generation of the Z10 processor. Again, we extended the KM and the KMC instruction to perform AES 192 and AES 256, as well as DES and AES 128. We also extended the SHA algorithm so that we can now do SHA 512, which means we support the full SHA-2 suite within the hardware. So you can get the full performance impact or benefit of hashing on the CPAC-F hardware. Again, this is still only using clear key encryption. This is not doing secure keys. So the hardware is expecting to receive the key material in the clear. On slide 19, with GA3, which was the final generation of the Z10 processor, we implemented the protected key support. Now, to do that, you also have to have the Crypto Express 3 card installed and available, but we now support protected key. And MSA3 is still using the KM, the KMC instructions for encryption, and the KIMD and the KLMD for hashing. Those are all supported on that CPAC-F hardware. And finally, on slide 20, the Z196, we introduced MSA4. Now, we didn't add any new functionality to the KM, the KMC instructions. We actually introduced some new instructions that we'll see on the next chart, but they provide some additional chaining operations. Again, I want to emphasize, on the CPAC-F hardware, this is the functionality you have. Symmetric encryption using either DES or AES, and hashing. If you want to do RSA or elliptic curve, the CPAC-F will not help you with that. The CPAC-F does nothing with RSA or elliptic curve. It doesn't do anything in terms of the ATM pin processing. That's got to be done on the Crypto Express card. So we're going to see it again a little bit later on, but the functionality on the CPAC-F is very fast, but there's not a lot of functionality on the CPAC-F hardware. So let's touch on those new chaining options a little bit. And this is a similar chart to one we saw last month where I talked about chaining. And just to refresh your memory, when you're doing the most basic level encryption uses something called ECB mode, or electronic codebook mode. And the idea with ECB mode is you take a block of data and you encrypt it with a key and you get some ciphertext. Well, the problem is if you have repeating data in your message, every time you encrypt a block, the same block, you'll get the same ciphertext. So if you're encrypting maybe a Word document with lots of spaces at the beginning or the end of the line, or in the example here, this picture of tux, you've got lots of repeating white space and black space and some yellow space for the feet and the bill. If I take a block of black pixels and encrypt them with the key, I'll get some ciphertext. And 3 lines farther down in the picture, if I have the same repeating block of black pixels, I will get the same ciphertext. So you can see there in the middle that the image of tux, there's really not a lot of security there. There's some encryption, but there's not a lot of security there. So to get around that, we use what's called chaining or cipher block chaining. And with cipher block chaining, what happens is when you perform one encryption operation, we will take a result of that operation and apply that to the next block of data that's going to be encrypted. So this example today is using a diagram for output feedback mode. I think the one we used last month was cipher feedback mode, and it just has to do with where you pull the intermediate operation from. So when we encrypt the first 8 bytes of data, we're going to pull part of that result out and apply that to the next block of data before we encrypt it. And then the result of that operation, we're going to pull an intermediate result out and apply that to the third block of encryption. So what happens is, as you go through the message, as you encrypt the message, the ciphertext is going to depend on everything that went on before it. And as you can see there in that third diagram at the bottom, the encryption is much, much stronger. Now, on the Z196, we introduced MSA4, which provides cipher message with cipher feedback mode, cipher message with counter, and cipher message with output feedback mode. So these are basically additional instructions on the CPAC-F that will perform this encryption with chaining and do it all at hardware speeds. Prior to this support, if you wanted to do chaining, we could do that, but ICSF would get involved in making sure that the intermediate results were captured and applied to the next block. So you should see some pretty significant performance benefits because we're now doing it all in hardware, so it should be much faster. Now, we're going to go to slide 22, and I'm going to take a quick drink here. I want to talk a little bit, not so much about performance, well, a little bit about performance. A common question that I get is, how do I know if I'm using the CPAC-F hardware? How can I tell? And, you know, since it provides instructions like the KM instruction, you can't go in and count how many move character instructions you're executing. Similarly, you can't count how many KM instructions or KMC instructions that you're executing. However, totally unrelated to crypto, with the Z10, we implemented something, or we made available a new facility called the CPU measurement facility. Now, what this was a technology that we were using internally in the labs to try and get some experience and get some performance data. And we've just externalized this with the Z10 and made it available to customers. So the technology's been enabled so you can use it. And you still can't count individual instructions. However, we do start collecting some counters on selected functions. And some of those selected functions include the crypto technology. So you'll see down in the chart at the bottom, we have counters for the pseudo-random number generator. We have counters for SHA hashing, AES encryption, and DES encryption. Now, we don't provide granularity. You know, you can't tell I did, 3,000 operations with triple DES and 1,000 operations with single DES and 4,000 with AES. But we do just keep a count of how many times those instructions are executed in that function count block. There's also a cycle count, which we'll keep track of the number of cycles that were involved. And then we also keep track of blocked function and blocked cycle count. Now, if you go back to the Z10 and the Z196 and Z114, where we talked about the CPAC-F was shared between two CPs, if one CP was executing a KM instruction, the other CP could not use that KM instruction and it would be blocked. If that happened, it would show up here in the blocked count. And that reminds me of what I wanted to mention before when we talked about that chart. I know of no customers that ever had any performance problems because we were sharing the CPAC-F between two CPs. We never got any complaints. Those instructions were just so fast that the work was getting done. But if there was a case where one CP had to wait on the other CP, it would have showed up in this blocked count. Now with the ZEC12 today and the ZBC12, we're no longer sharing it, so I would expect the block counts to always be 0 on those machines. Now this data is actually recorded in an SMF 113 record, a Type 113 record. This chart actually comes from one of John Berg's charts. John Berg is one of the performance guys in the ATS, the same organization that I'm in. He has published some documentation on how to implement the CPU measurement facility, because it does a lot more than just count crypto instructions. He's documented how to enable it, how to set it up, how to capture the data. Once you have the data in the SMF Type 113 records, you can use MXG or whatever tools you use to process your SMF data to pull these counts out and look at how many times you're invoking these functions. I encourage you to go ahead and start doing that. When we talk about performance, I'll talk about some of the limitations in the performance monitoring today. What you can use this for is to start developing trends. As you roll out new crypto workloads, it would be useful to watch these counts and see how they grow over time. So I do encourage you to maybe have your performance people take a look at this functionality, make sure that's enabled, start collecting the 113 records so that you can get at least a measurement of how much is going on and then start looking at trends over time. I'm getting ready to bring this in for a landing. Slide 23. Again, what I'm trying to point out here is the limited functionality on the CPAC-F hardware. It only does hashing and DES encryption. If you look at all of the ICSF APIs that are available, there's almost, I think it's up to about 170, 140 now. ICSF APIs, only 8 of the ICSF APIs require or use the CPAC-F hardware. There are more APIs, there's 26 APIs that don't require any hardware. There's over 70 APIs that require the Crypto Express card. So in terms of the functionality provided, the CPACF is fairly limited. But what it does provide is clear key DES, AES encryption, and hashing that is very, very fast. When we talk about the Crypto Express cards next week or next month, we'll talk about the fact that it's significantly slower. Again, because that's an asynchronous operation where the work has to be routed out to the card, as opposed to these instructions that are running at CPU speeds on the general purpose engine itself. So with that, I'm going to wrap things up. I think all of these tech docs were in the presentation last month. However, the last bullet on there, the TC000066, is the reference material that John Berg has on that new CPU mainframe counter facility. He goes through the process of configuring it and getting things set up so that you can collect that data. So I would refer you to that tech doc. Again, you can take a look at the Principles of Operations manual for your machine and see what the instructions are that are available so that you can write your own assembler routines to invoke these instructions, or you can rely on the ICSF APIs. My partner, Ernie Noctegal, who also supports crypto out of ATS, he's published a couple tech docs that provide some samples on how to code the ICSF APIs and actually take advantage of the CPAC-F hardware. So you can take a look at those 2 tech docs. And again, what we focused on today was a little bit of the hardware in general, but focused on the CPAC-F hardware. That is the clear key hardware that's available with System Z. Next month, we're going to focus on the Crypto Express cards, the PCI cards that are available. We're going to talk a lot about the functionality that's there, as well as some of the performance aspects. We'll also look at some more of the HMC slides in terms of configuring that hardware. So with that, I'm going to turn things back over to Michelle. I'm also going to stop the recording, so if you've got any questions, feel free to bring them up now. Michelle?
All right, thank Greg, and I want to thank